Team, now this is a review on resistor, inductor, capacitor circuits, and we are going to do this problem together. So I just wanted to put this graph in here so you can see what is going on for our RLC circuit, because it's different from the LC circuit. In an LC circuit, everything will be in resonance. There's no loss in charge. Everything will be continuing. However, for an LC circuit or for an LRC circuit, since we have the resistor here, and the resistor dissipates energy, and let's say that this EMF, there's no driving frequency involved, then we would have something to this effect. That we would be losing charge, losing voltage, because our energy is being dissipated in the system. Okay, so that's what an RLC circuit is looking like. It looks like when it comes graphically. Now for part A, it says calculate the root mean squared current through the RLC circuit. This is basically what you guys did in lab 4. So basically, we have our equation, I RMS, and we are given the voltage RMS here. So E, or EMF RMS, over R squared plus, the square root of R squared plus the reactance of the inductor minus the reactance of the capacitor squared. Remember, the reactance of the inductor is equal to the angular frequency times the inductance. And this signifies the opposition of current due to the inductor. Then we have the reactance of the capacitor, which is angular frequency times capacitance, and this is the opposition of current due to the capacitance. The combination of the resistor, the capacitors, and the inductor creates the impedance, and that impedance is this equation at the bottom right here, or right here. This is impedance. Okay, so basically you're already given the frequency, you're given the capacitance, and you are also given the inductance and resistor. So in this situation, it is only plug and chug for part A. Part B, luckily for us, it is the phase angle between the current and the voltage in this circuit. So basically, our equation is right here. And it is saying that, let's say that we have voltage right here, and voltage is like this. Something to that effect. That's voltage. Let me put V over time. And then we have current that goes something to this effect. So the phase is the distance, or the phase angle is from here to here. That is phi. Okay? So let me write this down, and we already have the equation involved. Just so you know, it's very simple, straightforward. I think RLC circuits are basically the simplest out of the two. I think one of the harder ones is actually RC. But yeah, this is the phase angle. Done. You have the equation for it complete. Now let's go for the calculate the average power dissipated through the resistor. You have two ways of doing this. We can go about it using our PRC, where it says the average power is equal to the I RMS squared times the resistor of the RLC circuit. But we also have, just in case, the power average equals the EMS, like the ERMS, EMF RMS, times the IRMS. I know that, like these RMS are driving me crazy. Times cosine of the phase angle. But check this out. We solve for the phase angle, so we can just plug the phase angle in here, and we get the average power. You can go about it both ways because you did solve for IRMS, but in case that you didn't solve for IRMS and you don't want to solve for impedance, you can go straight. Actually, no. Yeah, if you're not getting a resistor but you're getting an IRMS, then this is a good way to go for it. There are two ways. I'm just trying to show you. And then finally, it says calculate the resonant frequency at which power is maximized. So, just for your knowledge book, resonant frequency of an RLC circuit is the frequency at which the amplitude of the current is at a maximum, and the current would oscillate if it's not driven by a voltage source. So basically, if you take, like, it's like I was saying before, if you take off this, the EMF, and you take off the resistor, then just having these two will create a resonant frequency. And that resonant frequency is angular frequency equals 1 over LC, inductor capacitance. And if we want to get more with the frequency, it would be 2 pi over the angular frequency. And voila. I believe this concludes our RLC circuit review.